Welcome to the Deep Dive, your shortcut to being truly well-informed on the cutting edge of innovation. Today we are taking a deep dive into something genuinely revolutionary, I think, in the world of music technology. It's a groundbreaking new system called MIDI-RWKV. Forget the idea of AI just churning out generic tunes. Imagine if artificial intelligence could truly understand your unique musical style, adapt to your precise creative needs, and actually help you fill in those tricky, missing musical gaps in your longer compositions. That's the bold promise, anyway, of MIDI-RWKV.
Yeah, it's a really fascinating area because, despite all the incredible advancements we've seen in AI music generation lately, a core problem has stubbornly remained for actual composers. These tools, they often feel kind of clunky, difficult to control, or simply lack the ability to truly integrate into a personal creative process. Composers struggle with iterating on specific sections, with maintaining fine-grained control, and especially with capturing that unique personal artistic touch across, say, an entire piece.
Okay, let's unpack this a bit. Picture an AI that doesn't just generate a whole piece for you from scratch, right? But acts more like a smart, highly collaborative partner. A system designed from the ground up for personalizable, multi-track, long context that seems key and precisely controllable music and filling. Our mission today is to understand how this innovative model, built on the incredibly efficient RWKV7 linear architecture, aims to revolutionize computer-assisted composition for you, the creative mind.
Exactly. And this model specifically focuses on three main contributions that really stand out in the research paper. First, just introducing MIDI-RWKV itself. That's big. Second, it demonstrates how its novel state tuning method achieves superior performance for personalizing the AI to your style. We'll get into what that means. And third, it shows that it significantly outperforms existing approaches, particularly when it comes to that long context music and filling, which honestly has been a major bottleneck for a while.
Right. So if AI music tools have been around for a bit, what's the critical, persistent gap between what AI can do with music and what you as a composer actually need in your creative workflow? Like, what are those lingering frustrations that MIDI-RWKV is truly trying to solve here?
Well, the main limitation, I think, stems from how most existing systems operate. Many focus on end-to-end generation, meaning they produce a complete composition or maybe a lengthy continuation. And while that can be impressive as a demo, it's really difficult for composers to actively use in their day-to-day, iterative back-and-forth creative processes. If you want to change just a specific chord progression in the middle or regenerate a bridge section, most traditional autoregressive models, they just can't easily go back and regenerate just that section without potentially messing up everything else. It's kind of like trying to rewrite a single paragraph in a novel without touching any other part of the book, practically impossible with a lot of the current tools.
Yeah, I can totally see how that would be incredibly frustrating. It sounds almost like a fire and forget tool, but what if you're, not happy with the first shot?
Exactly. And another big issue lies with the current infilling models, which do allow that selective regeneration. The problem is, they often suffer from really limited context windows. Music, just like language, has these long-range dependencies, right? A melodic motif from 20 bars ago might influence what needs to happen now. Or a harmonic progression might demand a specific resolution many measures later. These older models, they often struggle to capture that larger musical architecture. Plus, they frequently lack sufficient controllability and personalizability. We even saw concrete feedback from the 2020 AI songwriting contest, where systems were frequently found to be, and I quote, insufficiently steerable or context-aware. Basically, artists said they couldn't guide them effectively.
That makes perfect sense. Artists don't just want generic music. They want generative systems that can, mimic their own style. They want their creative partner to sound like them. So this raises an important question. How does MIDI-RWKV specifically attempt to bridge this gap, addressing those very pain points for you, the composer?
Right. MIDI-RWKV directly tackles these limitations through four key design specifications. First, it's long context awareness. This is achieved using that RWKV7 architecture we mentioned, allowing it to capture significantly longer range dependencies than previous models. Think of it as having a much, much longer musical memory. Second, it supports selective regeneration through an adapted bar fill representation, which lets it focus precisely on generating specific masked sections you designate. Third, controllability is built right in. It incorporates numerical attribute controls that let you guide the generation, like telling it to play more or fewer notes per bar. And finally, personalizability. This comes from a novel state tuning method, which is particularly effective in small data regimes, meaning it can actually learn your style even from just a few examples of your own music. Pretty neat.
Okay, that's a lot to chew on. Building on existing ideas but pushing them forward. What I find truly remarkable, as you hinted, is how MIDI-RWKV isn't starting from scratch. It's cleverly building on decades of AI music research. Let's delve into that fascinating lineage a bit. How did they bring these innovations together? What foundational work, what previous models led to this breakthrough?
Well, the core concept here is infilling. It's actually quite similar to in-painting, in-image generation, where you reconstruct missing visual information from the surrounding context. In music, it means filling in the blanks, basically. And in a way, basic autoregressive generation, just predicting the next note based on past ones, can even be seen as a special case of infilling, just without any future context to guide it. Early approaches to music infilling used a whole range of neural networks. Things like VAEs, variational autoencoders, which are good at generating variations, or CNNs, convolutional neural networks often used for images but adapted for musical patterns, and RNNs, recurrent neural networks, which are naturally suited for sequences like melody and harmony. These paved the way, sure, but they were largely limited to single tracks. As the field matured, the powerful transformer architecture became dominant, leading to more capable multi-track systems.
Right, the transformer era. So how does MIDI-RWKV compare to those more established multi-track systems like, say, MIDI-Mistral or MMM that some of our listeners might have encountered?
That's a great question because when we look at models like MIDI-Mistral, MIDI-GPT, and MMM, MIDI-RWKV really does distinguish itself in some key ways. For instance, while those models generally had strict maximum context lengths, often around 2048, or maybe any 192 tokens, essentially a finite amount of musical memory, MIDI-RWKV aims for effectively infinite context length. That's because of its inherent RNN nature during inference. Imagine trying to compose a whole symphony. MIDI-Mistral might only remember up to about 8,000 musical events, maybe a few minutes of music. MIDI-RWKV, because of its unique RWKV design, can theoretically remember the entire symphony you're working on as it generates. That's potentially a huge game changer for really long compositions. Also, while MIDI-GPT and M&M offered some attribute controls, like controlling note density, MIDI-Mistral didn't offer any at all. MIDI-RWKV embraces robust controls as a core feature. And the crucial distinction is that MIDI-RWKV uses single-section infilling. It focuses on one contiguous masked section at a time. This lets it sort of concentrate its processing power more effectively, unlike some older systems that might try to fill scattered gaps within their limited windows.
That continuity seems vital for musical flow. And you mentioned controllability as a key feature. Why is that so crucial for a generative model to be truly useful for artists?
Oh, controllability is absolutely paramount. Without it, you're just kind of a passive observer of the AI's output, right? You hit generate and hope for the best. For a model to be a genuine creative assistant, you need to be able to tell it what kind of music you want in a specific section. We've seen other models, like MMM and Melandro's Composer's Assistant, offer controls for things like note density, polyphony, maybe even a rough style parameter. MIDI-RWKV builds on this by allowing pretty precise control over note density, note duration types, and polyphony within the specific bars you're infilling. This means you're not just hoping the AI gets it right, you're actively guiding it.
Gotcha. And building on that, the drive for personalization became a key focus. You mentioned artists wanting systems that can mimic their own style, not just produce generic stuff. But if you're an individual artist, you might only have, I don't know, a handful of your own compositions. How do you personalize a massive AI with such limited data?
Yeah, this is where what's called a small data approach becomes incredibly relevant. Because you're right, individual artists typically don't have huge data sets of their own work. This concept has been explored in visual arts and in music, with systems like Melandro's Composer's Assistant 2 already showing that low data fine-tuning for artists is viable. MIDI-RWKV aims to push this even further. Now, to make all this long context personalization possible, there was a fundamental shift needed in the AI architecture itself. Think about how powerful traditional AI models are, like transformers. Huge leap forward, but they have a big bottleneck. Their processing power, the computation, kind of explodes as your musical sequence gets longer. Imagine a chef who, for every new ingredient, has to meticulously retaste every single ingredient already in the pot, all mixed together, before deciding what to add next. That's the quadratic problem owing to time and space complexity, and it makes really long compositions computationally unmanageable or very slow. Linear architectures like RWKV7 are fundamentally different. They're more like a chef who instantly knows the current state of the dish, the flavor profile right now, and can quickly add the next ingredient, no matter how many have gone in already. This linear efficiency and complexity is why MIDI-RWKV can handle those epic long musical contexts and also train much faster.
RWKV7 specifically integrates something called the delta rule into its state updates, which essentially helps it maintain a very expressive internal memory needed for complex sequences like music.
That chef analogy really clarifies the efficiency gain there. Makes sense. And speaking of architecture, you mentioned a clever technique called initial state tuning is also critical here. Can you break that down? What is it and how does it play into RWKV7?
Absolutely. State tuning is a technique that's actually been around since the 90s for these recurrent neural networks, or RNNs. The idea is simple, but pretty powerful. Instead of just starting the model's internal memory, its hidden state, at 0 every time, you optimize it. You find the perfect starting point for its internal trajectory, tailored to the task. This is particularly beneficial for modern RNNs with really expressive hidden states like RWKV7 because it allows the model to capture more subtle, transient musical behaviors and better adapt its internal dynamics to specific contexts or styles. The RWKV PEFT library has been pioneering this specifically for RWKV models, and MIDI-RWKV leverages this technique as really a cornerstone of its personalization capabilities.
Okay, fascinating stuff under the hood. All right, now let's truly dive into the nuts and bolts. Given those ambitious goals-long contexts, selective regeneration, controllability, and personalization, how exactly did the researchers design MIDI-RWKV to actually hit them? What's the implementation look like?
Right, so the system was explicitly engineered with those 4 goals as its guiding principles, from the ground up. For data representation, MIDI-RWKV uses the MIDI-Talk library and REMI encoding. REMI is a fairly standard way now to represent multi-track MIDI files. It basically turns musical events like when a note starts, its pitch, its velocity, how long it lasts, into a linear sequence of tokens, much like words in a sentence for language models. Now, to manage the sequence length and the overall vocabulary size, they employ something called byte pair encoding, or BPE. Think of BPE like a smart compression algorithm, but for sequences. It finds common sequences of musical events, like a particular chord voicing followed by a rest, and turns them into single new, unique tokens. This significantly reduces the total sequence length the model has to process, making it more efficient, and allows for a much richer musical vocabulary. They augmented it from about 663 basic tokens up to 16,000 unique tokens this way.
Wow, okay, so it's essentially making the musical language more compact and efficient for the AI to understand and generate. What about that bar fill representation for selective regeneration? How does it actually tell the AI what to fill in?
Yeah, that's central to the selective regeneration piece. It's adapted from some earlier work by Enz and Pasquier, and is actually quite intuitive. When you want specific bars to be infilled by the AI, those sections in the sequence are simply masked out by special infill bar tokens. The different musical tracks in your composition are structured with track start and track end tokens, along with program tokens to specify instruments like acoustic grand piano or drums. Standard stuff. The entire process score then concatenates all these tracks, followed by the specific section you want the AI to infill, which is clearly marked off by fill bar start and fill bar end tokens, so the model knows exactly where to generate. And a crucial design choice here, as I mentioned, is what they call single-section infilling. Unlike some prior systems that might mask multiple disconnected sections simultaneously, maybe within a limited context window, MIDI-RWKV infills only one contiguous masked section per run. The idea is that this allows the model to really concentrate its attention, so to speak, on that single infilling task. This is critical for achieving those much longer effective context lengths. You could technically infill more complex multi-section patterns by making multiple calls to the model, but doing it all at once might leak unmasked content, potentially giving the model unintended information or just making it harder for it to focus properly.
Right, that makes a lot of sense for maintaining focus and coherence. And for a composer, those attribute controls you mentioned earlier are probably invaluable. How are they actually implemented within the model's input?
Yeah, for controllability, MIDI-RWKV lets you control 3 specific musical attributes per bar you're generating. You can specify note density, which is roughly the number of notes you want in that bar, ranging from 1 up to 18 or even more. You can specify note duration using binary tokens to indicate the presence of certain note types like whole, half, quarter notes, and so on. And polyphony, which specifies the minimum and maximum number of simultaneous notes allowed in that bar. These attributes are calculated using the MIDI-Talk library, and then they're injected as special tokens right after each bar separation token during the training process. This basically teaches the model to associate these numerical values with specific musical characteristics, allowing you, the user, to explicitly guide the generation during inference time. As for the core architecture, the generative model uses RWKV7. We talked about why it was chosen over the traditional transformer because it offers comparable or even better performance for sequence modeling, but with much more efficient training and inference.
And critically, as an RNN, RWKV7 is uniquely suited for that state tuning method we discussed, making it ideal for personalization. The model itself is optimized using a standard technique called categorical cross-entropy loss, which is very common for training models that predict the next token in a sequence.
Okay, that sounds like a really powerful combination of established techniques and new twists. Can you walk us through the experimental process? How was the model actually trained and then used for inference, like in practice?
Sure. In terms of experimental procedures, the base model was first trained on the massive GigaMIDI dataset. That's over 1 million MIDI files, a really vast ocean of musical data. During pre-processing, the MIDI files are carefully treated. Pitches are randomly transposed, which helps the model generalize across different keys, and tracks within a file are sometimes reordered to ensure the model learns diverse patterns. When creating the infilling sections for training, a random number of bars is chosen to be masked. They're careful to avoid masking totally empty measures, as that could cause the model to just learn to generate silence, which isn't very useful. Context bars of music before and after the mask section are selected to be the greatest number that fits within the training sequence length, which was set at 2048 tokens. This rigorous data prep is really key to the model's final robustness. Now, for inference, that's when you, the user, want to generate music. You provide your existing score, you specify a particular track ID you want to work on a context length C, and those attribute controls to the bar's N you want the AI to infill. Those N-specified bars are masked out in the input sequence, and C context bars are extracted from both before and after the gap. And here's where RWKV7's RNN nature really shines during inference. Because its hidden state size is constant regardless of sequence length, it effectively allows for an unlimited window size at inference time. This means it can process an N plus 2C window far exceeding its 2048 token training context. So if you're trying to fill in, say, 8 bars and 8 with 32 bars of context on either side, C32, it can actually process that entire 72-bar window, 8 plus 32 plus 32, efficiently. Pretty cool extrapolation. There's also a custom sampling loop that allows for fine-grained control over generation parameters like temperature, which affects creativity, or randomness, and repetition penalty to prevent it from getting stuck in loops. It even intelligently rejects some undesirable sequences, like 2 consecutive bar-known tokens, which would mean an empty measure, something composers rarely want when asking for a generated fill.
Fascinating how it combines the fixed training context with that effectively unlimited RNN inference context. Best of both worlds, maybe. And then there's that personalized aspect you mentioned earlier. How does that state tuning work in practice for personalization, and why is it supposed to be so effective, especially with small data sets?
Right, that's where the core idea of state tuning for personalization comes in, and it's quite elegant, really. Given a small inspiration set of your own musical examples, maybe just a few of your tracks or MIDI files, MIDI-RWKV optimizes only the initial state vectors of the model's layers. Crucially, the main massive model parameters, the millions of weights, are completely frozen. They don't change. This is a monumental difference compared to full fine-tuning, which retrains everything, or even other efficient techniques like LoRa, low-rank adaptation, which still modify millions of model weights. State tuning optimizes significantly fewer parameters, maybe just tens or hundreds of thousands, compared to millions for LoRa, or the base model. It doesn't really teach the model new fundamental musical structures. The base model already learned those from GigaMIDI. Instead, you could say it extracts information the model has already learned and biases its starting point. Think of it this way. The base model knows the entire universe of music it was trained on. State tuning simply biases the model's internal trajectory, its thinking process right from the start, to align better with your specific style. This is incredibly effective for these big foundation models like MIDI-RWKV, which have been pre-trained on diverse datasets. They've learned fundamental musical principles. State tuning then allows the model to apply those principles in a way that matches your unique stylistic variations, even if it only sees a very small sample of your work.
Okay, that makes a lot of sense, nudging the existing knowledge rather than retraining everything. So we've covered the goals, the clever engineering, the underlying architecture, but the real question is, what were the results? How did MIDI-RWKV actually stack up against other models when they tested it? What did the numbers, and importantly, what did human ears actually say about its performance for composers like you?
Right, let's get to the proof in the pudding. Looking at the numbers first. The base model, as mentioned, was trained for about 32 hours on a single powerful GPU, ending up with around 38 million parameters. Not huge by today's standards, but significant. For the personalization experiments, they used 99 randomly selected songs from the POP909 dataset, focusing just on the melody track for clarity and testing. This really simulates that small data approach, which is super relevant for individual composers. Now, state tuning, in comparison to training the base model, was remarkably efficient. It optimized about 294,000 parameters in roughly 4 minutes and showed very stable performance dynamics even with a relatively high learning rate. They also compared it to LoRa baselines. Depending on the rank, LoRa optimized between 331,000 and 2.7 million parameters, taking about 4.5 to 6 minutes. So state tuning was definitely a very fast and parameter-efficient way to personalize. To rigorously test its capabilities, they measured MIDI-RWKV against other models using a few key objective benchmarks or metrics. Think of these as scientific ways to gauge how well it preserved the style of the input context, content preservation, how accurately it maintained the original rhythm or groove similarity, and whether it kept the tonality consistent, pitch class histogram, entropy difference. And the results were pretty striking. Across the board, MIDI-RWKV didn't just perform well, it significantly outperformed previous models like MIDI-Mistral, especially when handling those long musical passages. For instance, MIDI-Mistral, a primary competitor, really struggled or failed completely on longer contexts, like an 8-bar infilling task that required looking at 32 bars of context on either side. Its limited token memory just couldn't handle it. MIDI-RWKV, on the other hand, demonstrated this remarkable ability to extrapolate over long musical contexts, consistently maintaining rhythm and tonality even with very long inputs. This clearly shows it's much better at capturing those crucial long-range dependencies in music.
That's a huge step forward, especially for anyone working on longer-form compositions. So if we connect this to the bigger picture of personalization, how well did that state tuning actually work in these objective tests compared to, say, LoRa or just the base model?
Right, connecting back to personalization. The Vine tuning comparison also showed really strong results for state tuning. Generally, state tuning performed objectively better than both the base model and LoRa for those metrics related to style, content preservation, rhythm, groove similarity, and tonality, PCHE, in this low-sample regime. For example, looking at 8-bar infilling tasks, state tuning achieved a content preservation score of 23.52 versus only 0.287 for the base model, and groove similarity was 0.908 versus 0.884. So it demonstrably did a better job of preserving the artist's specific style, rhythm, and tonality based on the small inspiration set. Interestingly, the reconstruction scores, or F1 scores, showed less significant differences. The author suggests this might be because F1 isn't always the best metric for musical diversity or creativity. Sometimes a perfect reconstruction isn't what you want. And a crucial conclusion they draw in the paper is that, despite its performance benefits, state tuning should not be considered a replacement for LoRa. LoRa, remember, modifies a small number of model weights, while state tuning affects the initial internal state. Because they target different things, the methods are actually complementary and can be used in conjunction. So you could potentially layer both techniques for even better, more nuanced personalization.
Ah, okay. So they're not mutually exclusive, which is great news for composers looking for maximum flexibility. That's really interesting.
And how effective were those explicit attribute controls, like telling it how many notes per bar? Did it listen?
Yeah, the categorical controls for note density, note duration, and polyphony were found to be broadly effective. For instance, the generated note density was, on average, very close to the desired amount, roughly 1 note per bar difference from the requested target. So it generally listens. However, the researchers offer a kind of nuanced perspective here. They suggest that a 100% success rate, where the model always hits the exact number you requested, might not always be desirable if it conflicts with overall musical coherence or sounds unnatural. The model needs to balance strictly adhering to the prompt with maintaining musicality and sounding, well, like good music.
Right, makes sense. Of course, music is inherently subjective. Numbers only tell part of the story. So this raises an important question. What did human listeners actually prefer in the subjective evaluation? Did the objective improvements translate to human ears liking it more?
Exactly. That's why subjective tests are so critical. As the paper notes, objective metrics are often incomplete measures of quality for creative tasks like music generation. A good infilling might diverge significantly from the original ground truth, but still be musically coherent and pleasing to listen to. So for the listening test, they had 28 participants rank 4 anonymized clips for 5 different 8-bar infills taken from that POP909 dataset. For each infill, participants heard the original human-composed piece, a version generated by the base MIDI-RWKV model, a version from a LoRa fine-tuned model, and the version from the state-tuned model. They had to rank them from best to worst. The results? Well, first, there was a clear preference for the original human-composed music. Perhaps not surprising, human creativity still reigns supreme.
Okay. Good to know we're not obsolete yet.
Not yet. But among the AI-generated options, the state-tuned model showed significant improvements over both the base model and LoRa fine-tuning, statistically speaking. It received the most second-place rankings, indicating that listeners found it to have better musical coherence and generally preferred it over the other AI methods. Interestingly, there was no significant difference in preference found between the base model and the LoRa fine-tuned version in this particular subjective test. Some common qualitative feedback from the listeners included things like minor rhythmic inconsistencies sometimes, and occasionally melodies that felt a bit boring or uninteresting in the generated content. So, still room for improvement, but state tuning was definitely preferred.
That's really encouraging for the personalization aspect then. So summing this all up, what does this mean for you, the composer, listening right now? MIDI-RWKV is clearly a significant step forward, offering personalized, long context, and controllable music infilling. It sounds really promising. But, like you said, no technology is perfect. What are its acknowledged limitations based on the research, and where do we go from here? What's next?
Yeah, indeed, MIDI-RWKV makes some really significant strides. It delivers on that long context awareness, the selective regeneration, the controllability, and especially that effective personalization via state tuning, all while maintaining pretty impressive efficiency thanks to RWKV7. It's a powerful potential tool. However, the authors are very candid and upfront about its current limitations, which honestly also point towards exciting avenues for future work. First, like any model trained on a large dataset, it inherits biases from GigaMIDI. Certain musical styles or instruments might be over or underrepresented in its output. Standard AI problem. Second, its prompt format currently restricts infilling to contiguous sections and generally requires symmetric context, meaning you need musical material both before and after the gap you want to fill. That might not fit every compositional workflow. You might need workarounds like multiple calls, which adds computation. Third, while its context extrapolation and inference is impressive, the actual training context length was 2048 tokens. This might still limit its direct usability for, say, extremely long context situations of full songs with 10 or more tracks, without breaking them down. Additionally, the number and granularity of the attribute controls, while useful, are somewhat limited compared to the very nuanced guidance a professional composer might desire. Also, the model currently needs you to externally provide those attribute controls for each bar you want generated. This kind of reduces its generative freedom if you actually want it to come up with its own ideas for density or polyphony sometimes. State tuning, while powerful, might perform less well on highly experimental or unusual compositional styles that are really far outside its pre-training distribution. It works best by adapting patterns it already broadly understands. And it's important to reiterate, it's complementary to LoRa, not a replacement for it if you need to modify weights. And finally, a couple of practical points. The system isn't yet real-time due to inference latency.
And the whole RWKV ecosystem, while growing fast, is still less mature than the transformer ecosystem, which can make direct DAW integration, like with tools like Calliope, a bit more challenging right now, though that's actively being worked on. And as we discussed, the evaluation itself has limits. Objective metrics are incomplete, and the subjective test scope was necessarily limited. These are all natural next steps for researchers in the field.
That's a good, honest assessment. And it also raises an important question. What about the ethical implications of such powerful generative tools, especially ones that can mimic style so well?
That's a crucial point the paper touches on as well. There are definitely outstanding ethical and legal questions concerning the generation of music that exactly matches copyrighted work. And specifically with state tuning, because it's designed to mimic style effectively from small data sets, it raises the risk of users fine-tuning the model to impersonate the styles of others, including potential copyrighted work. That's something the community needs to grapple with as these tools become more powerful and accessible.
Absolutely. A conversation we need to keep having. Hashtag outro book. What's really fascinating here, though, is the sheer potential. MIDI-RWKV seems to take us much closer to a truly collaborative AI partner in music. For you, the composer, it potentially means less wrestling with technical limitations and maybe more time for pure creativity. The aha moment for me is realizing that AI isn't just generating music for you, but potentially with you in your unique voice, leveraging its vast knowledge while respecting your individual style and specific creative needs.
Yeah, if we connect this to the bigger picture, this work really lays a strong foundation for future advancements in human AI musical co-creation. It emphasizes the role of AI as a powerful tool to augment human expression, not necessarily replace it, by understanding and adapting to individual artistic nuances and workflows much better than before.
So, what does this all mean for the future? As these AI music tools become more sophisticated, more controllable, more personalizable, how might our very definition of composition or originality evolve? And maybe even more exciting, what new forms of creative expression will emerge when humans and AI can truly dance together, not just as master and tool, but perhaps as more equal partners in the creative process? Something to mull over. We invite you to explore the possibilities.